Okay, so here we have to explain how the monobromination of benzene helped us learn more about the structure of benzene and how it works. So as we can see right here, that's benzene, and then we can also see the result of the monobromination of benzene as well. So one of the key things that we learned from this experiment was that benzene behaves like a Lewis base and donates its electrons, and is also known as an electrophile. Okay, so moving over for the second one is to explain how the second bromination of benzene help us, learn more about the structure of benzene. So as we can see right here, this is benzene, and then if we go further with another bromination, we have three options right here, three products. So we got the ortho, the meta, and the para positions of the product. So main key things to take away from this is that halogens are definitely electron withdrawing groups that favor the ortho and the para positions. So that's why the meta product is not going to be major at all, and they also act as deactivators. Okay, so as we can see right here, when HCl is added to 1,3-butadiene, we have this end result, end product, and the beginning product over here. So the key thing right here is a high temperature or room temperature. At this temperature, the formation of the least stable alkene is favored, as we can see right here, by resonance, and this is what we end up with right here. So as the positive charge in one side and the negative at the other, chlorine actually attacks that positive area, and that's how we end up with this result. As I said, key thing here is the high temperature or room temperature that favors the least stable alkene. Okay, so as we can see right here, is to explain why an acyl group like the one found in acetophenone is a meta director. So as we can see right here, the acyl group is a ring deactivator and is electron withdrawing by resonance. So this makes the meta location the electron containing area as opposed to the ortho and para. So as we can see right here, due to resonance, we see a positive charge coming up right here at the ortho location and over here at the para location. And if we do further resonance, then we see the other ortho location right there being electron deficient. So definitely due to resonance, carbocation intermediates are formed in the ortho and para locations, and the ring is less likely to be substituted at these locations. Okay, so now we have to draw the complete mechanism to convert benzene into M-nitrobenzoaldehyde. So we start right here with benzene, of course, and the first step is gonna be to do Friedel-Crafts acylation right here. That's what we see on this step right here, and this step right here, and this is the product that is formed. So after that, we are gonna have some nucleophilic substitution here that's gonna give us the next product here, and after that, the last step is gonna be nitration over here. So the key thing is to remember that the acyl group right there is meta director. That's why we end up with M-nitrobenzoaldehyde. So it's a meta director right there. Okay, so lastly, the last thing that we're going to do here is to carry out the following synthesis. So we start with benzene, and then we end up with bromoaniline. So starting material, of course, is benzene. The first thing that we're going to do is to carry out some bromination, and that's why we have this intermediate, this bromobenzene right here. Next thing we're going to do is to do some nitration, but as we can see, we end up with this, and since bromine is an ortho and para director, that's why we get them at opposite sides of the benzene ring. Next thing that we're gonna do, so we don't want a nitro group, we want an amine group. So we're gonna carry out some reduction right here, and that's why we end up with p-bromoaniline.